So in order for us to get a full understanding of this different way that we measure angles, we're going to go through that investigation to begin with. So if you take a moment to read over the first question. So we're being asked to determine the sector of a circle of radius 10 if the sector is 30 degrees. So let's break down from that what we know. So we're being asked, we have been given the circle. We know that the circle has a radius of 10 centimeters. And we are going to rotate, so the portion of our circle that we're looking at is about a 30-degree angle that we have here. And so it is asking us the area of this sector, right? So we're being asked to find the area of that. So if I shade it, right, so how many centimeters square will that take up? Will our sector take up? And so to think about this, first let's consider what is the area of our full circle. So our area of the full circle, you'll recall, is our pi r squared. And in this case, our radius is 10. So the area of this full circle would be 100 pi centimeters squared. And we're going to leave our answer exact. But we're not being asked for the area of the full circle. Instead, we're being asked for a portion of that. So a sector. So really what we're being asked is we want a proportion of 30 degrees of our circle. So if we think about that, 30 degrees out of a regular full rotation, which is 360 degrees, we are being asked to find the area of 1/12 of our circle. So I can go ahead and find the area of my sector is going to be 1/12 of the full area of the circle. And we can say that that's approximately 26 centimeters squared. We're not too concerned right now with our rounding. So that's just, again, letting us kind of start to work with some background information just on the relationship between parts of a circle and its whole. And in this example, we were dealing with the area. And if we take to read our example 2, we're being asked to determine the arc length of a sector of a circle of radius 20 if the sector angle is 140. So what we're being asked when we're talking about arc length, so determine the arc length, is how long is the arc that is created by our rotation of 140 degrees. So again, let's begin by using the information that we know. I know I have a radius of 20 centimeters. I know that I am rotating 140 degrees. And again, I am being asked to calculate the arc length. So how long is the arc that is created by that rotation? So I want you to pause for a moment and think about how has this question changed from our previous question? And how can you go about answering this question to find out what that arc length would be? So in this case, we're looking for our circumference. And so we can recall that our formula for a circumference of a circle is either pi diameter or 2 pi r. So I can find out the circumference of the entire circle that I have here. And I find out that that circumference is 40 pi centimeters. And then I go, okay, I don't want the full circumference of my circle. Rather, I only want to know what the arc length is that is created by a 140-degree angle. So I have 140 degrees over my 360, and what I notice is I need the circumference for 7/18 of my circle. So my arc length, and I'm going to write out arc length because if I just write A equals, that could be quite confusing in terms of we're not looking for our area, is to calculate this arc length, I'm going to have 7/18 of my full rotation, and that full rotation is 70 pi centimeters. So we should get down to approximately 49 centimeters is the length that it takes for this circle to rotate 140 degrees. So in our example 3, I'm going to read through it first and then we'll start to break down what it's saying. So it's asking us to find the measure of the angle. So we're finding the measure of the angle that's subtended at the center of our circle. So we know that's in our middle of our circle, and it's going to be between 2 radii with radius r and an arc length of r. So there's a lot going on in this question so far. So let's first break down what that looks like. So we know we have a radius r. We are being asked to find the measure of an angle. So in this case, we're being asked to find the value of our angle. And it has a radius r and it has an arc length of r. So slightly different from the questions we've been doing in our first 2 examples, because now we're being asked to find the value of theta. However, we know that we're using arc length. So we've also done calculations where we have arc length compared to our full circle, the full circumference. And we've also been comparing our angle of our sector to a full turn angle. So if we think about what we've already done in our other questions, we took whatever our sector size was, so that sector angle, and we compared it to the full turn, so to the full 360 degrees. We did that in our last question when we compared 140 degrees to 360 degrees. And in this case, because we're dealing with arc length, we know we're going to be comparing it to the circumference of the circle. So we're comparing the arc length that we've been given to the entire circumference of that circle. So we've really kind of come up with a bit of a formula here, but not a formula that you need to memorize or need to, it's just what we're kind of putting down our thoughts of what we've been doing, right? So we've been looking at part of the circle to its whole. So if we think about that in this scenario, and in this scenario, we don't have any values given to us. We have a theta and we have unknowns, which are represented by r. And we notice, though, that our radius and our arc length are both represented by capital R, which means they are the same length. So let's start to fill in, based on our background information from the previous 2 questions, what we know. So our sector angle here is theta. We know we have a full turn. We compare that to our full 360 degrees. We have our arc length here is r. And we know our circumference is represented by 2 pi r. And so we know circumference is 2 pi r. And in this case, our r is a capital R, because that's the value that we have here for r. So 2 pi r. what you'll notice is we can divide out our r's. And if I multiply out the 360, so really, I'll take a step back. I could have had 360 r times 2 pi r. The r's divide out. I would get 360 degrees over 2 pi. I can reduce that further, and I get 180 degrees divided by pi. If you were to sub that into your calculator, 180 degrees divided by pi, you will get an answer of approximately 67.3 degrees. The value, and when you type that into your calculator, I want you to use your pi button, not 3.14. So your actual pi button. Okay. This here, which we will go into more detail, this here is the value of 1 radian. So 1 radian is equal to 57.3 degrees. And we are, by the end of the day today, going to be thinking about radians, not in terms of degrees, but in terms of radians. But the value of 1 radian in degrees is 57.3 degrees. Okay, so I understand at this moment, we probably aren't understanding the significance of what that means, and that's okay. But we want to just understand that the value of 1 radian in degrees is 57.3 degrees. So if we go back up a step and look at it not in terms of degrees, we have 180 over pi, which I'm going to further explain to you as well. Okay, but I want us to look at one other thing. So I want us to look at why this makes sense. So if we look at our diagram, I'm hoping you can kind of see that our sector kind of looks like a triangle, right? So if you're looking back up at that diagram, it kind of looks like a triangle. I understand it's not fully a triangle because it's rounded at the bottom, okay? But it kind of looks like a triangle. And if we're looking at that triangle, we know that, so if I were to make it a triangle, I realize it's not a triangle, but we know that if this was r and this was our arc length was r, we know that this side here is also our radius. So that would also be labeled with an r. And so I'm hoping when you look at that, you realize, wow, that does kind of look like a triangle. That would be an equilateral triangle. I know that an equilateral triangle all has interior angles of 60 degrees. Well, that's kind of getting close to this 57.3 that I have. But I also recognize that it's what we have in our diagram is not a triangle, that it's curved. So in order for us to curve this, we have to pinch in these sides a bit. And if I pinch in those sides a bit, that angle inside there is going to get smaller. And when I pinch in those sides and that angle gets a bit smaller, we can probably look at that and see, wow, okay, that's getting closer to that 57.3 degrees that we have here in our angle that's made when we have a radius of r and an arc length of r. Okay, so we've created this really meaningful angle, and what you'll notice, part of why it's also meaningful is because there were no values given on this circle, right? It's for r and r. So it doesn't matter what the size of that radius is. We know that if we create a sector and the arc length is equal to its radius, we will always get an angle of 57.3 degrees. Right? So for any triangle, for any circle where the radius is the same length as the arc length, an angle of 57.3 degrees is formed. Okay, so this is a really meaningful new measurement, right? So, but right now, when we're thinking about it as 57.3 degrees, we're still thinking about it in degrees. And we want to start to put that into radians. Okay? So that's where we're going to go to next. So first, let's make sure we get down that notation. So 1 radian, this new meaningful measurement that we have. So a radian is created. We know the value of a radian. It's the measure of an angle, which is subtended at the center of the circle. So that's just telling us the angle that's in the middle of the circle, by an arc equal in length to the radius of a circle. So our arc length is equal to the radius. So that is so important here, right? So for any circle, if the arc length and the radius are equal, then the angle that is formed is the value of 1 radian. So what we want to keep in mind here is radian measure is the ratio of the arc length of a circle to its radius. So a radian measure is equal to the arc length divided by its radius. So if we have an arc length, so let's say we had a radius of 5 and an arc length of 5, we know what would be created at that, the angle that is created in that circle, in that sector, would be 1 radian. If our arc length was 10, and our radius was 5, our arc length is 10 and our radius is 5, we know the angle that is created there is 2 radians or 2 rads. So just some extra information there to help us to think about that. Okay, so I can use a different, if our radius is 4 and our arc length is 12, then we know we have rotated 3 radians. Okay. So 1 radian is equal to when our arc length and our radius are equal in length. All right, so right now we're still kind of thinking about our radians in terms of degrees. So we're going to start to transition from that. So again, we know that a radian is equal to our arc length divided by our radius. So let's take what we know about our degrees and start to turn those into radians, okay? And then eventually we want to start to think about things in terms of radians and stop having to turn them to degrees to then turn them to radians. So let's start with this. We know a full rotation is 360 degrees. So if I fully rotate in a circle, a full rotation is 360 degrees. Well, we know we describe radians in terms of our arc length divided by our radius. So if I go the arc length of an entire circle, I know that I'm rotating a full 2 pi r, and I know that my radius is r. Well, if I simplify that, I find out that 360 degrees is equal to 2 pi radians. So that would be a full rotation. So we would represent a full rotation in radians as 2 pi. If we want to then think about, well, what would a half rotation be? So if I rotate on my unit circle, what would be a half rotation? Well, let's take these values and divide them by half. 180 degrees is half of 360, and half of 2 pi is pi. So we would describe a half rotation as pi radians. So here we have degrees, and here we have in terms of radians. So what we could say when we look at this is we can look at this and go, well then, what would 1 radian be, right? So if we have 180 is equal to pi, if I want to find out what 1 radian is, right now I have pi radians. If I want to think about what 1 radian is equal to, that would give me 180 divided by pi. Right? If I wanted to take my radians and find out what 1 radian was, I divide both sides by pi. Pi divided by pi is 1. And I find out that 1 radian is equal to 180 degrees. So in radian notation, 1 radian is equal to 180 over pi. What you'll notice is if we want to write that in degrees, if you were to type into your calculator 180 divided by pi, you would get approximately 57.3 degrees, right? So we can tell what 1 radian is in radian notation, and we also know what 1 radian is in degrees. So we're going to look at our unit circle, and we're going to hopefully get a better understanding of this. So again, if you're still at the eek, not 100% sure, no worries. I'm hoping we will get you there, okay? So, and if you're also not overly familiar with your unit circle, that's okay. We do want to become familiar with this and be familiar with these values as we continue to build over the next few days, okay? So our unit circle. Let's first start. We're going to first start with degrees because I think it's important that we start with what you guys know, okay? And eventually we will move away from degrees, but we need to start with what we know in order to build on that understanding. So you know here we have 0. All right, we start at 0. We rotate. A positive rotation is up through the first quadrant. I can rotate around to 180 degrees. And then if I finish that rotation, I get back to my starting point. So that would be 0 or 360 degrees. We know that half of 180 degrees is 90 degrees. We know that a quarter of 180 degrees is 45 degrees. So these would all go up by 45. So 45, 90. I have 135 degrees if I go on my quarters. 225 degrees. So I'm just rotating around. So this is opening up as I rotate. This would be 225 degrees. If I kept rotating, this would be 270 degrees. If I rotate another 45 degrees, that would get me to 315 degrees. And then I would get back to my 360 degrees, right? So you guys are used to that on your 45-degree angles. I then can look at my 30-degree angles. So this would be 30, Another 30 gives me that 60-degree angle that we're used to. Another 30 gets me to 90. Another 30 gets me to 120. Another 30 gets me to 150, to 180, right? So I'm just rotating and going, if I were to rotate 210 degrees, well, you guys would rotate into that third quadrant, right? To get to 210 degrees, you would rotate past 180, and you would continue to rotate 30 degrees past that to 210 degrees. If you wanted to rotate to 240 degrees, well, we know that we're going to continue to rotate. We're still in that third quadrant. If I asked you to draw me a diagram with a terminal arm at 300 degrees, well, you would have started at your initial arm here. You would have rotated into that fourth quadrant and drawn that that's approximately where 300 degrees is. So again, these are all just our base using what our knowledge is of our 30, 60, 45, and 90 degrees, what that would look like for our unit circle. And we know starting at our initial arm and rotating up through that first quadrant gives us those positive values. So that's what we have for our degrees. So I'm hoping that looking at that, some of those key values do stand out to us, right? If I asked you to draw a 60-degree angle or a 135-degree angle, you would be able to rotate that into those quadrants and have an approximate idea of where that terminal arm would end. So this is what we know about a unit circle so far. Now let's start to convert this into our radians, okay? So we know that this is 0. We know half a rotation, we said, was pi. And then we know that if we go a full rotation, we said that that was 2 pi. So just so you can put in your minds as well, that means a half rotation is 3.14 approximately radians, right? Which when we think about that, again, 1 radian was about 57.3 degrees. So there's my 1 radian. And then I'd have my 2 radians, okay? And then our 3 and a bit radians that we have here, okay? So that is the value of pi, okay? Oops. So a full rotation would give us 6.28 radians, 2 times pi, okay? But again, I don't even want you to think about them in terms of approximates. I'm just hoping that that helps to connect some of our thoughts together. So if I asked you for your unit circle in radians, right away we should be able to locate our pi and our 2 pi. My next guess is it's probably going to be pretty fast for us to write what 90 degrees would be in radians, because I have pi, and if I cut that pi in half, I get pi by 2. And then, well, let's now think about, well, what would my 45-degree angles be? Well, if I have pi, so if I'm thinking about just this half rotation here, if I have pi units, if I cut that in 4, I get my 45-degree angles. So I have my pi by 4. This, if I were to continue to rotate, would be a 2 pi by 4, which simplifies to pi by 2. If I rotate another pi by 4, this would be my 3 pi by 4. And then I would get 4 pi by 4, which is just pi. If I continued to rotate and I had pi units plus another pi by 4, that's going to give me 5 pi by 4s. Another pi by 4 will give me 6 pi by 4s, which we can reduce to 3 pi by 2. Another pi by 4 will give me 7 pi by 4s. And then if I continue to rotate, I'm at an 8 pi by 4, which equals 2 pi. So what we're looking at with radians, we're just using fractions and parts of our whole to help us come up with what these angles are. So now we've dealt with our 45-degree angles. If we were to think about how do I get a 30-degree angle, we would say, well, we take our 180 divided by 30 gives me 6. So if I take my 180 and I divide it by 6, I'm going to get my 30-degree angle. So I have pi by 6. My 30-degree angle is 1/6 of 180. So we can say that that is a pi by 6. We can also look at it. Our 60-degree angle would be taking 180 and dividing it by 3 gets me my 60 degrees. So my 60-degree angle is a third of 180. So I can say it is pi by 3. So now you're used to your 30-degree angle. Well, now we're going to think about that as pi by 6. Well, if pi was 180, if I divide that by 6, I get 30. So I have pi by 6 gives me my 30-degree angle. Pi by 4 gives me a 45-degree angle. I'm taking 180 and I'm dividing it into quarters, which gives me 45. 180, if I divide that by 3, gets me a 60-degree angle. So my 60-degree angle in radians is pi by 3. So I'm hoping we're now starting to make that connection. If you're starting to make that connection now, that's good. Okay, we're getting to that spot of where we're going, okay, so it was a 30-degree angle. Now instead in radians, I'm just thinking about a 30-degree angle as pi by 6. I'm now thinking about a 45-degree angle as pi by 4. A 60-degree angle as pi by 3. So if we look at those acute angles in that first quadrant, those are really our base values. And we can use that knowledge to help us come up with the other angles on our unit circle. So what I'm hoping we'll notice is, so now let's start to build those other values. Let's start with our pi by 3 angle. So this is pi by 3. If I continue to rotate, this would give me 2 pi by 3. If I continue to rotate, that would give me 3 pi by 3, which is equal to pi. So that's one way we can think about this unit circle. However, what's going to help us in further questions as well is to think about our related acute angle. So I want you to hear, so this is correct. 120 degrees is equal to 2 pi by 3. So I can think about it in terms of I'm rotating and adding on a pi by 3, another pi by 3, another pi by 3, and I can continue to rotate on my unit circle that way, just adding along pi by 3s, which is what I showed you with our pi by 4s, okay? The other thing we can do is we can recognize that this angle here would also be the same as saying pi, a pi rotation, and if I subtract a pi by 3, so pi minus pi by 3 is 3 pi by 3 minus pi by 3 gives me 2 pi. Okay, so we can use that related acute angle to also help us. How can I continue on with my rotation? Well, same thing. Here, I can take pi and I can add my pi by 3, which will give me 4 pi by 3. For this angle here, I can use my related acute angle and say 2 pi, because if I've gone a full rotation, and then if I subtract a pi by 3, I know that that angle, if I subtract a pi by 3, is going to be 5 pi by 3. So we are just using our related acute angles to help us come up with these unit circles. And what you'll notice is, again, I could count around if I wanted to. I have 1 pi by 3, 2 pi by 3s, 3 pi by 3s, 4 pi by 3s, 5 pi by 3s, 6 pi by 3s. So I have rotated a full 2 pi. But how we come up with and how we remember where the location of those angles are, we can use our related acute angles to help us with that. And I think that might, with where we're going with this information, that might be the most helpful way for you to be able to identify these values. So let's continue, keep going on, because we have pi by 6s we have to deal with. So I have a 1 pi by 6. Technically, I think we can all see that pi by 3 would be the same as saying 2 pi by 6s, which reduces 2 pi by 3. 3 pi by 6, 4 pi by 6, and now here we could have counted out and said, well, that's a 5 pi by 6. Well, we really don't want to have to count around a full 5 pi by 6 in order to be able to calculate what that value is. So our other option is to take our half rotation of pi units and subtract a pi by 6. So if I take pi minus pi by 6, I know that that value, so if I were to give you this location and said that this angle here, this related acute angle is pi by 6, you could have just said, well, I have a rotation of pi minus pi by 6. That angle you've given me there, Miss Katie, is an angle rotation of 5 pi by 6. Okay? So that is why I'm showing it to you in this way. So again, let's continue on. Here, we have a full pi rotation plus a pi by 6. So we know that 210 degrees is really 7 pi by 6. And then over here, if we rotate a full 2 pi, we can say 2 pi minus pi by 6 will give me my 11 pi by 6. So that is our unit circle. So why does some of this matter? So when are we going to start to use this? We're going to start to use this for our special triangle. We're going to use this notation for now when we're sketching, and when we can convert between degrees and our radians. Okay, and so again, there's a lot of information that's happening here. I think the key bits for you to keep in mind is our special triangles that used to be 30 degrees, right? We had a 30, 60, 90 triangle. We had a 45, 45, 90 triangle. Those angles that made up those special triangles, instead of now 30, 60, 90, 45 degrees, we have pi by 6s, pi by 4s, pi by 3s, and pi by 2s. So again, we have 0 to pi to come around to 2 pi. So 2 pi is a full rotation. Just south 360 degrees is a full rotation. I have half of 2 pi is pi. Half of 2 pi is pi, which is why it's a half rotation. Half of pi is pi by 2, which gives me those quarter rotations. Okay. So before we move on to what I wanted for our next slide, what I just want you to be able to see. So if I go back to our unit circle, right? So that's where now, instead of me asking you to draw for me where a terminal arm would be for a 210-degree angle, instead I am asking you for 7 pi by 6, which when we're dealing with our pi by 6s, pi by 4s, pi by 3s, it actually becomes a more efficient method in order to be able to show our solutions. Is when might we start to use this? So if I were to give you a question like this and asked you, and I said that this was a pi by 3 angle here, but I wanted to know what the value of that rotation is, you would be able to tell me that the value of theta is equal to 4 pi by 3. Or if I asked you and I said, draw for me where 7 pi by 6 is located, so where would the terminal arm be for that value? You would be able to say, I've rotated 6 pi by 6, and I have one more pi by 6 rotation, and that rotation would get me to 7 pi by 6. So the next step to kind of make sure that we have a good understanding of what is radian measure is if we can convert between radians and convert between degrees. So if I want to convert this, really, in order to not change the value of 45 degrees, I want to multiply this by 1, right? Because if I multiply a number by 1, I haven't changed the value of that number. But multiplying 45 degrees just by a 1 isn't going to change the form that I'm reading it in. So if I instead, I'm hoping we can all agree that pi and 180 are equal, right? Pi and 180 are equal. That we're trying to convert, so I do recognize that we're working with different units here, but I'm working with 1. So pi over 180 degrees, so I'm multiplying this by 1 because pi and 180 are equal. And when I do that, I get pi over 4. So I get pi by 4. So we want to choose this form that includes degrees and radians. That way we are able to convert from degrees to radians. And we know that pi and 180 represent the same value. So pi divided by 180 will equal 1. And we are trying to choose a form that includes degrees and radians. In this next example, I have pi by 2. And I want to turn that into degrees because currently it's in radians. So I want to use a different form. So instead of pi over 180, I want to compare 180 over pi. How did I know that's the form I wanted to use? Well, I want my pi's to divide out, and I'm left with 180 over 2, which gives me my 90 degrees. So I wanted to divide out that radian so that now it was written in degrees, right? So we're trying to convert from degrees or radians here. Something to be mindful of. Whatever unit you want to convert to, put that unit on top. Okay, so if I want to go from degrees to radians, I am going to multiply it by pi over 180 because I want to turn it into radians. So I'm going to make sure my radians are on top. If I want to turn from radians to degrees, I'm going to multiply it by 180 over pi because I'm trying to turn it into degrees. And so when we look at that last example there, I have 4 radians. I'm asking you to convert forms. So we want to turn it into degrees. So I'm going to multiply by 180 over pi. My radians will divide out, and we can write this as an approximate right now to 229.18 degrees, which I'm hoping, so again, 4 radians is approximately 229.18 degrees. So just to kind of bring it all together, that I'm hoping we're grasping this concept. So there's a lot to think about here, right? There's our unit circle to think about, and then there's actually the thought of what is the value of our radian and what is the size of that. So if we think about 4 radians, well, if a half rotation is approximately 3.14, and half of that then is approximately 1.57, our 4 radians is going to take us into that third quadrant. So we're in our third quadrant. We're told that that's, when we calculate, around 229.18 degrees. Well, if this is 180 degrees and this is 270 degrees, then that location should be in our third quadrant. So I'm hoping you can see that 4 radians, so if this is 3.14 radians, we know we have to have slightly more than that, and 229 degrees would rotate us into that third quadrant between our 180 degrees and our 270 degrees. So in fact, 4 radians is equal to approximately 229.18 degrees. We can also double check that because we know that the value of 1 radian in degrees is 57.3 degrees. So 4 times 57.3 degrees should get us that value there. So I'm hoping that that helps to, again, summarize and connect a bunch of the different thoughts that we've talked about today. And we're going to end just on one final example to really see if we kind of have come full circle here to understand this concept, this lesson that we've been doing today. Okay, so find the length of the arc of a circle with radius of 5 centimeters and an angle of 2 radians. So I'm going to give you a minute or two. I want you to come up with something that's some type of solution on how you can find the length of the arc of a circle that has a radius of 5 and an angle of 2 radians. Okay, and there's more than one way that we can think about that, but I want you to think about something now. So some of us might have gone back to the beginning and said, all right, I know I have my circle. I have a radius of 5 centimeters. Centimeters. And I have an angle of 2 radians. So some of us might have gone back to there, totally fine, and we started to work through what we did earlier, where you went, okay, I have 2 radians over a full rotation, which would be 2 pi radians. And so that would be my full rotation. So that's I have 2 over 2 pi, so that's this sector that I'm looking for. My circumference is 2 pi r. You divided those out, and you got that you had 10 centimeters, right? So you might have gone back to the beginning and went, this is what I'm understanding, perfectly fine. Or you also might have looked at that and said, okay, I know that the relationship for a radian is the relationship between the arc length compared to the radius. And that when the arc length and the radius, if those had been the same, I get the value of 1 radian. Well, in this case, you might have said, well, I know my arc length. I'm trying to find that. I know that I have a radius of 5 and an angle of 2 radians. So my arc length must be 10 centimeters. Okay. Another way to think about that, a third way, maybe that came across in your mind, was you said, okay, I have a radius of 5. I know that the rotation of 1 radian would mean I have an arc length of 5. So the rotation then of 2 radians would mean I have an arc length of 10. Either way, with all of these answers, we should notice that we have an arc length of 10 centimeters. So there's a lot to digest in today's lesson, right? We've come up with a whole new unit of measure. So we've come up with that 1 radian. So what's so special about this unit of radian measure is 1 radian, regardless of the size of the circle, when the radius and the arc length are the exact same length, the angle that is created is the value of 1 radian. So therefore, our measure of radians can be talked about the arc length compared to the radius, which we see in this example. We also use that information to convert from degrees to radians. So we said, okay, normally a full rotation would be 360 degrees. Well, instead, we used our knowledge of circumference and said, well, that could mean, though, that instead in radians, a full rotation is 2 pi. So a half rotation in radians is pi. And then we use that information to come up with our unit circle. So we covered a lot today about radians. So again, what is a radian? What do we know about the relationship that creates a radian? Well, we look at the arc length compared to the radius, and we've also now written it in our unit circle in terms of measures for our angles that we can then use moving forward. So take some time to look back over your note. It's going to take you some time to digest parts of this lesson, and you have some practice questions that you can be working on. We do want to be able to think about the relationship, like I was mentioning, in terms of where is 5 pi by 3 located? What is our most efficient way and our best way of understanding to write where the angle of 5 pi by 3 is located, or the angle of 7 pi by 6, right? So when you're looking at your unit circle, we want to look at it in terms of, can I compare that back to pi plus pi by 6, pi minus pi by 6, right? Can that help me when determining my angles? So that is our lesson for today. You have your practice questions are posted, and if you guys have any questions, I'm happy to answer them.